The universe is expanding. That much is settled. Dark energy pushes galaxies apart, and the process is gentle, predictable, and completely safe. Unless one number is wrong. If the dark energy equation of state drops below -1, the expansion does not just continue. The expansion accelerates until space rips apart every galaxy, every star, every atom on a countdown that has already been calculated. The calculation belongs to Caldwell, Kamionkowski, and Weinberg. Published in 2003 under the title Phantom Energy and Cosmic Doomsday, the paper follows one variable through one equation. The solution maps a destruction timeline onto every structure in the universe, from the largest galaxy cluster down to a single proton, each assigned a specific moment of death. But the Big Rip is only one entry in a catalogue of endings. Physicists have now classified 4 distinct types of cosmic ending, and at least one requires no exotic physics at all. The question has never been whether the universe will end. The question is which ending the math selects, and whether a single number, one that no instrument has yet measured precisely enough, determines the answer. If you enjoy journeys that change how you see reality, hit that like button and subscribe. So where did that number come from? Before anyone could ask whether the universe will end violently, someone had to discover that the universe is accelerating at all. And that discovery arrived late, overturning a consensus that had held unchallenged for 7 decades. Gravity pulled matter together. Galaxies clumped into filaments and clusters. And for most of the 20th century, the only debate worth having was about how fast the brakes would work. Every model built between the late 1920s and the mid-1990s assumed, without exception, a single trajectory. Expansion was slowing down. Nobody questioned that assumption because the physics behind the deceleration was clean, elegant, and confirmed by decades of observation. The universe was expanding outward after the Big Bang, but gravity was dragging the expansion back. The only genuine open question was whether gravity would eventually win, reversing the expansion entirely, or merely slow the outward motion to a final coast. Edwin Hubble demonstrated in 1929 that distant galaxies recede from us. Recession velocities scale in proportion to the distance. A galaxy twice as far away moves roughly twice as fast. Hubble measured the relationship carefully, building evidence that space stretches uniformly in every direction. Alexander Friedmann, working from Einstein's field equations several years earlier, had already derived the mathematics governing a quantity called the scale factor. Think of the scale factor as a ruler, stretched across the entire cosmos, measuring how average distances between all points change with time. As the universe expands, the ruler stretches. As the expansion decelerates, the ruler stretches more and more slowly with each passing epoch. Georges Lemaitre then proposed that the expansion, run backward through time, traces to a single primordial moment. 3 contributions spanning 3 decades, all converging on one sweeping conclusion. The cosmos began in a hot, dense state and has been flying apart ever since. But that expansion carries a cost. Every kilogram of matter in existence exerts a gravitational pull on every other kilogram. That pull acts as a drag on the outward motion, and gravity never relents. The expansion does not proceed freely. Gravity fights the outward push second by second, and the cumulative effect over billions of years is enormous. Picture a ball thrown straight upward from the surface of the Earth. Gravity does not hold the ball instantly. Instead, gravity bleeds kinetic energy away, slowing the ascent by roughly 10 meters per second every second. The ball rises. The ball decelerates. And eventually, the ball either falls back or escapes to infinity, depending entirely on the strength of the throw. The Friedmann equations describe the cosmic expansion in nearly the same terms. All the mass and energy packed into the cosmos act together as a gravitational brake. Enough mass, and the expansion reverses entirely. The cosmos collapses inward in a scenario called the Big Crunch, essentially the Big Bang replayed in reverse. Every galaxy, every star, every atom falls back into a single point. Too little mass, and the outcome is the opposite. The expansion continues forever, but always bleeding momentum, always losing speed, always coasting toward absolute stillness, a state where the temperature of space barely differs from zero. For context, the critical density separating these two outcomes is astonishingly low, roughly 6 hydrogen atoms per cubic meter, a number so low that the air inside a single room on Earth contains, by a staggering margin, more particles than the average cubic meter of deep space. Below that threshold, the cosmos expands forever. Above that threshold, the cosmos eventually collapses back in on itself. The fate of trillions of galaxies depends, remarkably, on whether the average cubic meter of space contains 6 atoms or 7. Those were the only 2 options on the table. The Big Crunch or the eternal coast toward absolute stillness. No third ending existed. And for 7 decades, every cosmologist on Earth accepted that binary as complete. Here is what the entire field believed, confidently, before the late 1990s. Deceleration was real. Deceleration was guaranteed by the equations. The magnitude of the slowdown was the only open question remaining. Astronomers organized an entire generation of observational campaigns around that unknown. How fast were the brakes working? The answer reduced to a single number called Q0, the deceleration parameter. Think of Q0 as a speedometer for the cosmic brakes. A positive Q0 means expansion is losing speed. A large positive value means collapse looms on the cosmological horizon, perhaps only tens of billions of years away. Measuring Q0 required observing objects at enormous distances with enough precision to detect subtle curvature in the distance. Redshift relationship. For decades, the instruments fell short of the challenge. Scatter in the distance, measurements was too large, and the target signal was far too faint to extract cleanly. Telescopes could not reach deep enough, and the calibration tools were too crude to extract a clean measurement from the noise. But by the early 1990s, a breakthrough in supernova science transformed the playing field. Let us talk about Type 1, a supernovae, because the story of the Big Rip begins with a particular kind of exploding star. A Type 1, a supernova, is a thermonuclear explosion of a white dwarf star. White dwarfs are dense, dead remnants of spent stars, collapsed cores roughly the size of Earth, but carrying nearly the mass of the Sun. In a binary system, a white dwarf gradually accumulates matter from a companion star. The mass grows gram by gram, century after century, until the total crosses a critical threshold called the Chandrasekhar limit, roughly 1.4 solar masses. At that mass, the core ignites. Carbon and oxygen fuse in a runaway thermonuclear chain reaction, destroying the entire white dwarf in a matter of seconds. The burst of light from that destruction remains visible across billions of light years, outshining the entire host galaxy for weeks. To put the energy scale in perspective, a single Type 1, a supernova, releases in just a few seconds as much energy as the Sun will produce in total over the entire 10 billion year lifespan of the Sun. That output makes Type 1a events visible at distances where individual stars vanish entirely, and where even whole galaxies shrink to faint smudges on a detector. Why are Type 1 supernovae so valuable for cosmology? Because every explosion occurs near the same critical mass. Every explosion produces roughly the same peak luminosity. That uniformity turns each Type 1, a supernova, into a standardized candle, a cosmic distance marker visible across an enormous fraction of the observable universe. Measure the apparent brightness of a distant Type 1a event. Compare that brightness to the known intrinsic output, and the gap between the two numbers reveals the distance. Simple in concept, enormously powerful in application. But the technique requires a calibration correction, because not every Type 1a event is perfectly identical. Mark Phillips published that correction in 1993. Phillips showed that the remaining variation in peak brightness follows a reliable rule. Slowly fading supernovae tend to be slightly brighter than average, while rapidly fading ones tend to be slightly dimmer. Apply the Phillips correction, and the distance precision improves dramatically, reaching roughly 15% per individual event. At that precision, a sample of a few dozen high redshift supernovae becomes powerful enough to pin down the cosmic deceleration parameter. The tools were finally ready, and the race to measure Q0 could begin in earnest. Two independent teams launched programs to make the measurement. Brian Schmidt led the High-Z supernova search team observationally, based at Mount Stromlo Observatory in Australia. Adam Rees, leading the data analysis at UC Berkeley and subsequently at the Harvard-Smithsonian Center for Astrophysics, applied two independent fitting methods to the full sample and directed more than a dozen collaborators across 4 continents. The team's specialty was rapid follow-up, the ability to catch each newly discovered supernova near peak brightness before the light faded beyond useful reach. Saul Perlmutter, meanwhile, led the Supernova Cosmology Project at Lawrence Berkeley National Laboratory in California. Perlmutter built an automated detection pipeline, essentially a factory for finding distant supernovae, capable of discovering dozens per observing run. Where Schmidt led a nimble team, Perlmutter ran an industrial operation. The rivalry between the two groups was fierce. Each raced to accumulate enough data to pin down Q0 before the other could publish. That competition sharpened the science because neither team wanted the other to find a mistake in the analysis. Both teams expected to confirm the old consensus. Both expected a positive deceleration parameter, proving that gravity was winning the tug of war against expansion. The question was not whether the universe was decelerating. The question was how fast. Neither team was prepared for what the data actually showed, and neither team expected the answer to overturn 7 decades of settled physics. In 1998, Adam Rees and the High-Z team published results from 16 high redshift supernovae and 34 nearby comparison objects. The distant supernovae were too dim. Not catastrophically dim, not dim enough to suggest a gross calibration error, but consistently, event after event, the high redshift explosions appeared by 10 to 15% farther away than any decelerating model predicted. The entire framework, built over 70 years of cosmology, was pointing in the wrong direction. Using 2 separate light curve fitting methods, the High-Z team measured Q0 as negative. One method yielded 2.8 sigma confidence. A second, independent fitting technique, yielded 3.9 sigma, even stronger. Both pointed in the same deeply unsettling direction, and neither result was consistent with any form of deceleration. The deceleration parameter was not merely small or ambiguous. That parameter was negative. The expansion of the universe was not slowing down at all. Expansion was speeding up, running away from stillness, faster and faster with no indication of stopping. Before going public, the High-Z team spent months hunting for every conceivable source of systematic error. Consider the most obvious candidate first: interstellar dust. Dust between the supernovae and the telescopes could dim distant objects, mimicking the signal of extra distance. But dust also reddens the light passing through, and the multicolor photometry of each supernova showed no excess reddening. Dust was ruled out. Consider supernova evolution next. Physical changes in supernovae at higher redshifts could alter intrinsic brightness, but the spectral features of the distant explosions, examined line by line, matched the nearby population with no significant deviation. Evolution was ruled out. Gravitational lensing presented a third candidate. Mass concentrations between the observer and the supernova can magnify or demagnify individual events, but lensing effects average out across a large sample, and the acceleration signals survived the statistical averaging intact. Lensing was ruled out. Selection bias was the final suspect. Observers might preferentially detect brighter events at greater distances, skewing the sample toward anomalously luminous supernovae and mimicking the dimming expected from extra distance. But the survey detection thresholds were well characterized, the bias corrections were small, and the signal persisted after every correction was applied. Contamination from Type II supernovae, physically distinct explosions, could corrupt the sample. Spectroscopic confirmation ruled that channel out as well. Every systematic channel came back clean. Every test the team designed to kill the signal failed. The acceleration survived every attack thrown against the result. The Supernova Cosmology Project, working with different telescopes, different software, and a completely different supernova sample, published consistent results during that same year. For a flat universe, the statistical significance of a non-zero cosmological constant reached between 7 and 9 sigma. The probability that acceleration was a statistical fluke was vanishingly small. A pair of independent teams, using independent methods and independent datasets, reached the same conclusion. The expansion of the universe was not merely continuing, the expansion was accelerating. And that conclusion was deeply disturbing. To appreciate why, consider what acceleration demands from the underlying physics. In a decelerating universe, expansion is simply a leftover from the Big Bang. The outward motion is residual, gradually surrendering to gravity. No new physics is required. But acceleration demands an energy source actively pushing the expansion forward, an energy source possessing a property no ordinary form of matter has. That property is called negative pressure, and no known form of ordinary matter possesses the property. Ordinary matter generates positive pressure, and so does radiation. In general relativity, both positive pressure forms contribute to gravitational attraction. For expansion to accelerate rather than decelerate, an entirely new component is required. That component must generate enough negative pressure spread across the entire cosmos to overwhelm the combined attractive pull of every kilogram of ordinary and dark matter. Cosmologists gave that component a name, one that has since become the most famous unsolved term in all of modern science: dark energy. The energy accounting turned out to be striking. Observations of the cosmic microwave background, the afterglow of the Big Bang preserved as a faint glow permeating all of space, nailed down a critical constraint. The total energy density of the universe matches, within narrow margins, the density required for a geometrically flat cosmos. Break that total into pieces. Ordinary baryonic matter, the protons and neutrons composing stars, planets, and interstellar gas clouds, accounts for roughly 5%. Cold, dark matter, the invisible gravitational scaffolding holding galaxies and galaxy clusters in place, accounts for roughly 27%. And the remainder, a full 68%, belongs to dark energy, more than 2/3 of the cosmic energy budget. In other words, belongs to a force nobody had detected before the final years of the 20th century. The dominant component of the universe was invisible, unidentified, and entirely unexpected. Now the story turns. If dark energy behaves exactly like the cosmological constant, a concept Einstein proposed in 1917 and later abandoned, the consequences are well understood. A cosmological constant represents a fixed energy density woven into every cubic centimeter of space. The energy density per unit volume never dilutes. As space stretches, new vacuum appears, and each new cubic centimeter carries the same energy as every existing one. More space means more total energy, growing in perfect lockstep with the volume of the cosmos. The pressure associated with a cosmological constant is negative, and the ratio of pressure to energy density, labeled W, equals exactly -1. That single number is the dividing line for the entire documentary. Every scenario described from this point forward, every prediction, every countdown, hinges on where the true value of W sits relative to that threshold. Consider the weight of that. The fate of every atom in the universe, from here to the edge of the observable cosmos, hangs on that one number. A universe dominated by a cosmological constant at W equals -1 follows a specific and permanent trajectory. Expansion continues forever, accelerating gently as dark energy gradually overwhelms the fading influence of matter. Galaxies beyond the local gravitational neighborhood drift away. One by one, those galaxies cross the cosmological horizon, becoming permanently unreachable and permanently invisible. Stars exhaust their nuclear fuel over billions of years. White dwarfs cool into frozen husks of crystallized carbon. Black holes evaporate over timescales so vast that the numbers carry no human meaning, durations measured in powers of 10 that exceed by many orders of magnitude the particle count of the observable universe. Slowly, relentlessly, the cosmos settles into a state called de Sitter space. De Sitter space is an exponentially expanding void where the temperature of the cosmic background creeps toward absolute zero and never fully arrives. Entropy reaches a maximum. All meaningful activity ceases, and every atom assembled by gravity survives intact, untouched by the expansion forever. Heat death is bleak, but heat death is not violent. No galaxy is torn apart by the stretching of space, not a single star is ripped open, and no atom is split against the wishes of the strong nuclear force. The universe simply fades, gradually and gently, into an equilibrium from which no further change is possible. That quiet fade was the default expectation held by working cosmologists for years after the 1998 discovery. No violence, no disruption. The universe would end eventually in cold silence, and every structure assembled by gravity would survive that silence intact. That default model, sometimes called the lambda cold dark matter model, has survived every observational test thrown at the framework over the past quarter century. The cosmic microwave background power spectrum matches the prediction. Type 1, a supernova distances at increasingly high redshifts match. Baryon acoustic oscillations, rhythmic patterns in the galaxy distribution, reflecting sound waves from the early universe, match. Weak gravitational lensing surveys, mapping dark matter across broad patches of sky, match. All of the data permits W at -1. No observation demands a different value. But the cosmological constant is not the only mechanism capable of producing negative pressure. In that same pivotal year, Robert Caldwell, Rahul Dave, and Paul Steinhardt, all at the University of Pennsylvania, published a fundamentally different proposal for dark energy. Instead of a fixed energy density frozen at one value for all time, the trio described a dynamical scalar field, a quantum field pervading all of space that evolves over time. As the universe expands, the field rolls through a potential energy surface, and the energy density of the field changes along the way. A cosmological constant stays locked at a single value forever. A dynamical scalar field, by contrast, evolves, shifts, and potentially decays over cosmic time. Caldwell, Dave, and Steinhardt named the new component quintessence. The name borrows from the fifth element of Aristotelian philosophy, signaling a category distinct from baryonic matter, dark matter, radiation, and the cosmological constant. What makes quintessence different from a cosmological constant, in physical terms? As the scalar field evolves through the potential, the balance between kinetic and potential energy shifts, and the equation of state parameter W changes over time. For quintessence, W falls in the range between -1 and -1/3. Unlike the cosmological constant, quintessence energy density is not static. The density evolves as the universe expands, and future observations could, in principle, track that evolution directly by monitoring how cosmic acceleration changes over time. Caldwell, Dave, and Steinhardt showed that quintessence leaves two distinct fingerprints in the observational record. One fingerprint appears in the cosmic microwave background, angular power spectrum, the pattern of temperature fluctuations in the oldest light in the universe. A second appears in the matter power spectrum, measuring how mass is distributed across the cosmos. Those fingerprints break the near degeneracy between quintessence and a pure cosmological constant, where near degeneracy means the two models produce observations so similar that only precise measurements can separate them. Future experiments could, in principle, use those differences to determine which model the universe actually follows. And the practical takeaway from quintessence was reassuring. Whether dark energy turns out to be a cosmological constant at W equals -1, or quintessence with W between -1 and -1/3, the long-term fate of the universe remains qualitatively identical. Expansion accelerates. Galaxies drift apart over trillions of years. Stars burn out. But every atom survives. The cosmos fades slowly into cold silence, and no structure in the universe, from a galaxy supercluster hundreds of millions of light-years across, down to a single hydrogen atom, faces any threat from the expansion. That reassurance was the scientific consensus for 4 years. From 1998 through 2001, the debate over dark energy stayed safely within that comfortable range. Cosmological constant or quintessence, fixed energy density, or dynamic. The answer mattered for theoretical physics, but the answer did not change the ending of the cosmic story. Either way, the universe fades into silence. Either way, every atom endures indefinitely. And then, at Dartmouth College, a physicist asked a question nobody had bothered to raise before. The detail that changes the entire picture is this. General relativity does not treat W equals -1 as a wall, a floor, or any kind of barrier. The Friedman equations contain no clause forbidding values below that threshold. From a mathematical standpoint, W is simply a number on a continuous real line, free to take any value. -1 is not a boundary enforced by any known law. -1 is a convention, drawn on the number line because every value above the threshold produces familiar, well-behaved expansion histories. For decades, no one studied the territory below that convention. Cosmologists ignored the region, dismissed the possibility, and treated values below -1 as physically irrelevant. In 2002, Robert Caldwell examined that forbidden territory. Working from the physics department at Dartmouth, Caldwell constructed a dark energy model with W below -1. Caldwell published the results under a memorable title, A Phantom Menace, with a question mark and a deliberate nod to Star Wars. That question mark was intentional, and the physics behind the title was deadly serious. Caldwell named the new component phantom energy, and the name was chosen for a reason. At the mathematical level, phantom energy emerges from a scalar field with a reversed kinetic term. In a standard field, kinetic energy is positive, and the field rolls downhill through the potential energy surface like a ball descending a slope. Reverse the sign on the kinetic term, and the ball rolls uphill. The field gains energy as the universe expands, rather than losing energy. That reversal violates a principle called the dominant energy condition, one of the foundational constraints that physicists have relied on for decades to guarantee sensible behavior in general relativity. The dominant energy condition states, in plain terms, that energy density must always be greater than or equal to the magnitude of pressure. Phantom energy breaks that rule, and breaking that rule unlocks a deeply alarming property, a property that separates phantom energy from every other form of dark energy. The energy density of phantom dark energy grows as the universe expands. Not stays constant, as a cosmological constant does, not gradually decreases, as quintessence does, grows. Compare 3 scenarios to understand why that property is so dangerous. A cosmological constant keeps dark energy density flat, unchanging, regardless of how much the universe expands. Quintessence allows the density to decrease gradually as the scalar field rolls through the potential. But phantom energy inverts that trend completely. Every cubic meter of space contains more phantom energy today than yesterday. Tomorrow will bring more than today, and the increase never stops. That growth is not arbitrary. A precise scaling relation governs the behavior. Energy density evolves as the scale factor raised to a specific power determined by -3 multiplied by 1 plus W. Follow each case through the mathematics. At W equals -1, the exponent is 0 and density stays constant. Above -1, the exponent turns negative and dark energy density gradually falls as the cosmos stretches. But below -1, the exponent flips positive and density climbs. No ceiling stops the rise and no saturation mechanism slows the climb. The increase continues, accelerating without end. This distinction between the 3 cases is not academic. This distinction is existential. Caldwell did not file phantom energy away as an abstract curiosity. Instead, Caldwell tested the model against real data from the observational record. Using type 1, supernova distances, cosmic microwave background measurements, and the mass power spectrum, the analysis demonstrated convincingly that phantom models fit the available data just as comfortably as the cosmological constant, even with W below -1. No observation excluded phantom energy. No measurement disfavored the hypothesis. Constraint contours from the supernova data extended smoothly past the W equals -1 line, and values of W well into phantom territory were permitted cleanly without any tension in the fit. That tolerance carries enormous consequences. The most consequential distinction in all of cosmology, whether the universe fades into silence or rips apart violently, sits inside the current measurement, uncertainty on W. Put simply, the gap between a quiet ending and a violent ending is narrower by a significant margin than the error bars on the best available data. Modern constraints place W at approximately -1.03, plus or minus roughly 0.03. The central value sits slightly below -1 within phantom territory, but the error bar comfortably spans the cosmological constant value. Whether the true value of W rests exactly at -1, slightly above in quintessence territory, or slightly below in phantom territory, no existing instrument can resolve the answer. And that uncertainty is not a footnote to an academic debate. A narrow sliver of parameter space between W at -1 and W at -1.05 determines whether every atom endures for eternity or carries a precise, calculable expiration date. On one side of that sliver sits heat, death, the cold and quiet fade into de sitter space. On the other side sits a fate, previously unconsidered, that no physicist had seriously contemplated before the 2002 paper by Caldwell. A universe that does not merely expand, but accelerates without limit until space rips apart galaxies, then stars, then planets, then atoms, on a countdown that has already been computed and published in a peer-reviewed journal. The cosmological constant was safe. Quintessence was interesting but ultimately harmless. And then Caldwell asked, what happens when W drops below -1? The answer turned out to be the most violent prediction in the history of physics. What waited on the other side of W equals -1? In 2002, Robert Caldwell crossed the boundary. The math does not stop at the boundary. The math keeps going. And where the math goes from there, no previous cosmological model had ever followed. Robert Caldwell had established in 2002 that the phantom energy density exponent flips positive when W falls below -1. More expansion means more phantom energy. More phantom energy drives faster expansion. Density without ceiling, growth without limit. That much the field already knew by early 2003. What nobody had done was follow that growth forward epoch by epoch, all the way through the Friedmann equations to the final state. Caldwell, now working with Mark Kamionkowski and Nevin Weinberg of the California Institute of Technology, ran the calculation to the end. On February 25, 2003, the trio submitted the results under a title that left no room for ambiguity: Phantom Energy and Cosmic Doomsday. The word doomsday was not decorative. To understand what the paper revealed, the Friedmann equation is the starting point. The Friedmann equation is the master equation governing cosmic expansion. At the most basic level, the equation relates the expansion rate of the universe, a quantity called the Hubble parameter, to the total energy content packed into every cubic meter of space. Every form of energy contributes to that total. Ordinary matter, dark matter, radiation, and dark energy each enter the equation, and each carries a scaling law describing how the energy density of that component changes as the universe stretches. What exactly does a universe dominated by phantom energy look like, one epoch at a time? The previous act established that the exponent flips positive when W drops below -1. What Caldwell, Kamionkowski, and Weinberg added was the integration. Run the Friedmann equation forward with that positive exponent, solve for the scale factor as a function of time, and extract the result. Think of the compounding dynamic this way. A bank account with a positive interest rate compounds over time because each new balance generates more interest than the last balance did. Phantom energy density works identically. More space produces more energy, which drives more expansion, which produces more space. The critical difference from any ordinary compounding system is that there is no regulator, no reserve requirement, and no ceiling anywhere in the physics. The compounding never stops, and the rate of compounding accelerates with each new increment of space created. That positive exponent is the entire catastrophe. Caldwell, Kamionkowski, and Weinberg wrote the Friedmann equation for a phantom-dominated universe and solved for the scale factor as a function of time. The solution contained a feature no previous model of the cosmos had ever produced: the scale factor, the cosmic ruler measuring the average distance between all points in the universe, reaches infinity at a specific, calculable, finite moment in the future. Not after an unimaginable number of years, not in some abstract mathematical limit that never physically arrives. The timescale depends on the value of W and the current expansion rate, and for physically reasonable parameter values, the singularity arrives within a window that is, by cosmic standards, alarmingly close. For W equals -3/2, with the Hubble parameter set at 70 kilometers per second per megaparsec, the scale factor hits infinity approximately 22 billion years from now. To put that number in perspective, the universe is roughly 13.8 billion years old today. Under the phantom model with W at -3/2, the cosmos has already lived more than half of the total time allotted. The remaining lifespan, 22 billion years, is less than twice the current age. On the cosmic calendar, the universe is past noon, heading into a late afternoon with a hard deadline on the horizon. That finite moment, the instant when the scale factor diverges to infinity, is the big rip. But the singularity at the endpoint is not the fool's story, and not the most disturbing part of the calculation. Long before the scale factor reaches infinity, the growing dark energy density begins to overwhelm every other force in existence. The destruction proceeds one structure at a time, from the largest to the smallest, in a sequence that Caldwell, Kamionkowski, and Weinberg calculated with meticulous precision. Here is how the destruction unfolds. In general relativity, the gravitational source term is not simply mass, and not simply energy density alone. The source for the gravitational field includes a contribution from pressure, weighted by a factor of 3. The effective gravitational source density, the quantity that determines whether a region of space attracts or repels, equals the energy density plus 3 times the pressure. For ordinary matter, pressure is small compared to energy density, and the combined term is solidly positive. Positive source density means attractive gravity, and structures hold together. For phantom energy, the arithmetic flips. With W below -1, the pressure is more negative than the energy density, by a factor exceeding 1. When the energy density and 3 times the pressure are combined, the total turns negative. Negative source density means repulsive gravity. Instead of pulling structures together, phantom energy pushes structures apart from the inside. And here is the critical detail. As phantom energy density grows with the expanding universe, the repulsive push does not hold steady. The repulsion intensifies month after month, year after year, epoch after epoch. At some critical moment in the future, the repulsion inside any gravitationally bound system exceeds the gravitational attraction holding that system together. At that moment, the system unbinds. The bonds holding the structure together simply fail, overpowered by the relentless growth of dark energy, filling every cubic meter of the interior. The critical moment depends on the size, the mass, and the binding strength of the structure. Larger, more loosely bound systems fail first. Smaller, more tightly bound systems survive longer. The destruction proceeds in a strict hierarchy, from the most diffuse structures in the cosmos down to the most compact. What does that formula mean for every structure the cosmos has ever assembled? Caldwell, Kamionkowski, and Weinberg derived a formula of striking elegance relating the destruction time to the orbital period of the structure. A gravitationally bound system with a circular orbital period, P at the outer edge, becomes unbound at a time roughly equal to P, multiplied by a factor that depends only on W. The stripping occurs at many time units before the phantom singularity. Remarkably, the stripping time does not depend on the Hubble constant and does not depend on the total matter density of the universe. Only 2 numbers matter: the orbital period of the bound system and the equation of state parameter W. The simplicity of the formula is what makes the destruction countdown so devastatingly precise, and the precision is not approximate. Caldwell, Kamionkowski, and Weinberg did not produce a rough sketch or an order of magnitude estimate. The team produced an exact formula derived from the Friedmann equation applicable to any bound system for which the orbital period is known. Any astronomer, given the mass and orbital radius of any gravitationally bound system, can calculate the exact time before the phantom singularity at which the system fails. Every entry in the countdown that follows is a specific number drawn from the formula, applied to real astrophysical systems with real measured orbital periods. The countdown is not a metaphor for destruction. The countdown is a table of exact dates, referenced to the singularity, with every number calculated to the precision that general relativity and observational cosmology jointly support. Apply the formula to actual structures in the universe, using W equals -3/2, and the timeline emerges in full. The results, when mapped to actual structures, function less like a scientific data summary and more like an obituary for the cosmos. Galaxy clusters, the largest gravitationally bound structures in the observable universe, carry orbital periods measured in billions of years. Those clusters are stripped apart roughly 1 billion years before the phantom endpoint. Every filament of the cosmic web unravels, every supercluster dissolves. The hot intracluster medium, the diffuse plasma filling the space between member galaxies, begins to expand beyond the gravitational potential that held the plasma in place for billions of years. The dark matter halos, the invisible scaffolding that organized the baryonic matter into coherent configurations across cosmic time, lose structural coherence. Galaxies that had been gravitationally associated, trading gas and stars and triggering star formation across billions of years, lose the capacity for any further interaction. The largest collaborative structures the cosmos has ever assembled dissolve into independent, expanding clouds, each drifting outward with no future of gravitational contact. The architecture of the large-scale universe, assembled patiently over 13 billion years of gravitational collapse, disintegrates in a geological instant. Next comes the Milky Way. Our galaxy, a barred spiral spanning 100,000 light-years, containing roughly 200 billion stars, is torn apart roughly 60 million years before the singularity. Stars that have orbited the galactic center for billions of years, tracing stable paths through the disk and halo, are flung outward into expanding voids. Spiral arms unwind. The central bar dissolves. Sagittarius, A star, the supermassive black hole at the galactic core, loses the gravitational grip that has held the surrounding stellar population in orbit for the full history of the galaxy. 60 million years is not an abstraction. On Earth, 66 million years ago, the Cretaceous extinction had already occurred. Dinosaurs had just vanished. Mammals were beginning a radiation that would eventually produce primates, then hominids, then observers capable of calculating the destruction of the galaxy those observers inhabit. All of mammalian dominance on Earth, from the extinction of the dinosaurs to the present day, fits inside that window. 3 months before the end, the solar system unbinds. The gravitational hold of the sun, maintained continuously for 4.5 billion years across 8 planetary orbits, fails. Earth drifts away from the sun. Jupiter and Saturn, the gas giants, lose orbital coherence. The outer ice giants, Uranus and Neptune, are released from confinement. Each planet becomes a solitary object, moving through expanding space with no star to orbit, no system to anchor the trajectory, and no gravitational companion within reach. 3 months. Consider that interval. Humans have been organizing calendars, tracking seasons, marking time for thousands of years. A quarter of a year is a recognizable human unit. In 3 months, a civilization can launch a mission, negotiate a treaty, or watch a comet complete a full arc of the comet's orbit. 3 months is not an abstraction drawn from the deep past or the far future. 3 months is a duration that fits inside a single chapter of human experience. And in 3 months, the orbital architecture that has governed every planet, every moon, every asteroid, every comet in this solar system since the solar disk cooled 4.5 billion years ago collapses entirely. The sun does not explode. The sun does not die. Instead, the star simply loses gravitational authority over every cubic meter of the solar system as phantom energy density grows past the threshold where gravity can compete. 30 minutes before the phantom endpoint, Earth explodes. The planet does not drift apart gently or dissolve slowly into fragments. The expansion of space within the volume of the Earth exceeds the combined electromagnetic and gravitational forces holding rock, mantle, and core together. Earth is ripped open from the inside. Crust fractures along fault lines that no tectonic process created. The mantle separates into expanding fragments. Deep below, the iron core, compressed to enormous density by 4.5 billion years of gravitational pressure, loses cohesion and flies apart. Right now, in this moment, every atom beneath your feet is held in place by electromagnetic bonds. Those bonds resist the full weight of an entire planet pressing inward. In the final 30 minutes, those bonds lose the contest against the expansion of the space between them. And then the countdown enters the atomic domain. Roughly 10 to the power of -19 seconds before the singularity, 1/10 quintillionth of a second, the expansion of space within individual atoms exceeds the electromagnetic force, binding electrons to nuclei. Every atom in the universe ionizes. Every hydrogen atom, every carbon atom, every iron atom forged in the cores of dead stars loses the electron shell that defines chemical identity. Molecules that had survived the destruction of planets, the unbinding of solar systems, and the dissolution of galaxies finally break apart into isolated particles. In the final instance, the strong nuclear force fails. Protons and neutrons, held together inside atomic nuclei by the strongest force known to physics, are ripped apart. Nuclei forged during primordial nucleosynthesis, assembled in the first 3 minutes after the Big Bang, surviving for nearly 14 billion years through every catastrophe the cosmos has produced, disintegrate. And then, quarks lose confinement. The strong force which, under every laboratory condition ever created by human experimenters, has never released an isolated quark, succumbs to the expansion of space. Every quark becomes an isolated point, separated from every other particle by distances growing faster than any signal can bridge. The singularity arrives, and the scale factor reaches infinity. Energy density diverges, pressure diverges to negative infinity. The universe ends not in a whisper and not in a slow fade. The universe ends in a final, total, hierarchical dismantlement of every structure that gravity and electromagnetism and the nuclear forces ever assembled. Pause on the precision of the sequence for a moment. Caldwell, Kamionkowski, and Weinberg did not estimate these timescales, and the team did not approximate from analogy. The team solved a differential equation, applied the solution to known astrophysical systems, and extracted exact relationships: 1 billion years for galaxy clusters, 60 million years for the Milky Way, 3 months for the solar system, and 30 minutes for the Earth. 10 to the power of -19 seconds for individual atoms. All of those numbers emerge from the same formula, applied to different orbital periods, with no free parameters beyond W and the Hubble constant. The calculation is clean, the consequence is total, and the paper presenting those consequences was submitted to physical review letters with the word doomsday in the title. That word choice was not accidental. Consider the naming conventions. Brett McInnes had introduced the term Big Rip the year before, and Caldwell, Kamionkowski, and Weinberg adopted the name immediately. 1 year earlier still, Caldwell had titled the 2002 Phantom Energy paper A Phantom Menace, complete with a question mark and an unmistakable nod to Star Wars. The name stuck. Phantom cosmology, a discipline responsible for predicting the most violent ending in the history of physics, entered the scientific literature carrying titles borrowed from science fiction. Rigorous differential equations, paired with cinematic naming, suggest a community that takes the mathematics with absolute seriousness. and the branding only slightly less so. Now consider what the countdown reveals about the present moment. Caldwell, Kamionkowski, and Weinberg noted a striking consequence buried inside the destruction timeline. The phantom endpoint does not merely end the universe. The phantom endpoint ends the era of structure. Once phantom energy density grows large enough, gravitational instability ceases to function entirely. New structures cannot form. Galaxies cannot collapse from gas clouds, and stars cannot ignite from gravitational compression. Not a single planet can coalesce from a debris disk. The universe becomes perfectly homogeneous, stripped of every deviation from uniformity, every clump, every filament, every density contrast that gravity had spent billions of years assembling. That observation carries a profound consequence for every observer in the cosmos. Non-linear structure, meaning galaxies, stars, planets, organisms, and observers, can only exist during a narrow window of cosmic time. Before the current epoch, the cosmos was too hot and dense for structure to form. After the phantom countdown begins in earnest, the universe will be too disrupted for any structure to survive. The team noted with characteristic precision that no other time permits non-linear structures. Every galaxy that exists today, every star shining in every sky across the observable universe, every planet circling those stars, every living organism on any world, occupies a finite interval of cosmic history. The interval opened when the first structures condensed from the cooling primordial plasma, roughly 1 billion years after the Big Bang. If phantom energy is real, the interval closes when the growing dark energy density overwhelms gravitational binding everywhere, simultaneously, without exception. And this constraint applies universally, not merely to observers on Earth. Every civilization anywhere in the observable universe, whether technologically sophisticated or not, whether contacted or undiscovered, whether carbon-based or built from chemistry no human chemist has imagined, exists within this same window. The window is not an Earth-specific feature. The window is a hard constraint imposed by the Friedmann equation on any arrangement of matter complex enough to maintain internal structure against the expansion of space. Every observer in the universe, on whatever world, in whatever galaxy, exists within that window, only within that window. And the window has edges. The window is not a metaphor. The window is a mathematical consequence of the Friedmann equation, solved under phantom energy dominance, with boundary conditions set by observable parameters. And the width of that window, the total duration available for complexity and structure, depends entirely on the value of W of W. And what does any of this reasoning mean for the question of why observers exist at all? Caldwell, Kamionkowski, and Weinberg took the observation one step further. Their paper noted that the coincidence problem, the long-standing puzzle of why dark energy density and matter density happen to be comparable in the present epoch, takes on a different character under phantom energy. In a universe headed for the phantom singularity, the coincidence is not surprising at all. Observers can only exist during the narrow interval when matter has already condensed into structures, but phantom energy has not yet grown dominant enough to destroy those structures. We exist now, at a moment when dark energy and matter densities are roughly comparable, because this moment is simply the only window when existence is possible. That coincidence dissolves instantly. Selection, not luck, provides the answer. Why do we observe the universe at this particular moment? Because no other moment permits observers to exist. Under heat death, atoms endure forever. No expansion threatens the nuclear bonds. No force disrupts molecular structure. The cosmos simply fades gradually and without violence into a cold equilibrium. Under phantom energy dominance, atoms carry an expiration date. The difference between those two endings is a single exponent in a single equation, and the boundary separating them is a cliff, not a gradient. At W equals -1, atoms endure forever. Below -1, atoms expire on a schedule. In heat death, the atoms that form stars and planets and organisms survive the end of complexity. Isolated protons drift through an expanding void for timescales that make the current age of the universe look like a fraction of a second. The atoms persist. The structure is gone, but the matter endures. In the Big Rip, The matter does not endure. Every proton is ripped apart. Nothing survives the final 10 to the power of negative 19 seconds except isolated quarks, themselves then subject to the causal isolation that follows. The precision of the difference is what makes the uncertainty so uncomfortable. Consider one more layer of the calculation, because the mathematics reveals a feature, one that makes the phantom endpoint different from every cosmic catastrophe previously imagined. In the final moments before the singularity, individual particles become causally isolated. A particle separated from a neighbor by any distance greater than a specific threshold cannot send or receive any signal before the singularity arrives. Caldwell, Kamionkowski, and Weinberg calculated that threshold explicitly. The maximum distance over which two particles can communicate in the time remaining equals 3 times the remaining time interval multiplied by a ratio depending on W. As the singularity approaches, that distance shrinks towards 0. Light cannot cross the gap. No force can bridge the separation. Every particle in the universe becomes an island, isolated from every other particle, unable to interact, unable to communicate, unable to exert any influence on any neighbor. The causal isolation is total. The destruction extends beyond the physical into the informational. No record of any structure, no signal from any star, no trace of any observer can propagate between isolated points in the final instance. The universe does not merely die. The universe forgets. Every piece of information, encoded in every structure ever assembled by gravity, is dispersed beyond the reach of recovery. Every pattern, every relationship between particles that gave rise to atoms and molecules and planets and minds dissolves into a uniform field of isolated points with no access to any other point and no ability to reconstruct what came before. The erasure is absolute. The forgetting is total and permanent. That informational erasure, that final and total loss, is what separates the phantom endpoint from every other ending previously considered. Heat death is slow, quiet, and preserving. The Big Crunch, the old collapse scenario, is violent but concentrated, compressing all information into a single point where, in principle, nothing is lost. The Big Rip combines violence with dispersal, scattering every particle beyond the reach of every other particle, erasing not merely structures, but the very possibility of interaction between any 2 points in space. Caldwell, Kamionkowski, and Weinberg mapped the destruction from galaxy clusters down to atoms. But the Big Rip, devastating as the prediction was, turned out to be only one entry in a catalog of cosmic endings nobody expected. The Big Rip was only the beginning. Caldwell, Kamionkowski, and Weinberg had mapped one extinction pathway, phantom energy, with W below -1 scale factor to infinity, countdown from galaxy clusters to quarks. That pathway was terrifying enough, but phantom energy was not the only mechanism in all of known physics capable of producing a cosmic singularity. In the years following the 2003 Doomsday paper, a series of independent teams began cataloging the full range of futures the mathematics permitted. What emerged from that catalog was not reassuring. The cosmos had more ways to die than anyone had suspected before 2003. Some of those pathways required no exotic physics at all. John Barrow at the University of Cambridge published a paper in 2004 titled "Sudden Future Singularities." The title describes the result precisely. Barrow showed that under certain conditions permitted by the Friedmann equations, the universe can develop a singularity even when the dominant energy condition holds, even without phantom energy, even without W below -1. To appreciate what that means, recall the earlier framework. The dominant energy condition is a constraint on the relationship between energy density and pressure. A cosmological constant satisfies the condition exactly, sitting at the boundary. Quintessence satisfies the condition within the quintessence parameter range. Phantom energy violates the condition, which is why Caldwell flagged the violation as a warning sign. For decades, the dominant energy condition had served as a kind of physical fence, separating the safe territory of well-behaved dark energy models from the dangerous territory of phantom cosmology. Barrow stepped around that fence entirely. The Friedman equations govern the expansion rate and the expansion acceleration. A third derivative also exists, describing how the acceleration changes over time. Barrow demonstrated that singular behavior could arise in that third derivative and in higher derivatives of the scale factor, without anything unusual happening to the expansion rate or the energy density at the singularity moment. Scale factor stays finite. Energy density stays finite alongside the scale factor. The pressure, however, diverges. Pressure, technically a second derivative of the scale factor, can spike to infinity at a specific moment, even while every quantity a distant observer could directly measure stays perfectly well-behaved right up to the end. Barrow constructed an explicit mathematical model to demonstrate the point. The scale factor follows a trajectory described by three terms: a constant a power law growth term, scaling as time to the power q, and a second power law term scaling as the quantity time remaining to the power n. When n falls between 0 and 1, the second derivative of the scale factor, which governs the pressure, diverges at the moment the remaining time reaches 0. That moment is a genuine singularity. Pressure goes to infinity, and the universe reaches an endpoint that has no continuation in classical general relativity. What makes the Barrow singularity stranger than the Big Rip is, above all else, the absence of any observable warning. In the Big Rip, the destruction unfolds hierarchically and visibly. Galaxy clusters unbind first, on a timescale of billions of years, producing observable changes in large-scale structure. Stars are stripped from galaxies on million-year timescales, and any civilization capable of cosmological observation would watch the disruption approaching for an enormous stretch of time before the final moments arrived. No such pre-warning sequence exists in a Barrow sudden singularity. Expansion rate holds steady. Temperature of the cosmic microwave background continues cooling on the standard trajectory. Galaxies remain gravitationally bound. Stars continue nuclear fusion, and planets keep their orbits. Right up to the edge of the singularity, every observable in the cosmos behaves exactly as the standard cosmological model predicts. And then, at a specific finite moment, the pressure of the universe diverges to infinity. The universe ends not by tearing apart from the outside inward, as in the Big Rip, but by an internal pressure catastrophe with no advanced symptom detectable from any observable quantity. The equations simply refuse to continue. The full taxonomy of cosmic singularities arrived in 2005 from a collaboration between Shinichi Nojiri and Sergei Odintsov, who had been working on modified gravity and quantum cosmology since the early 2000s, and Shinji Chujikawa, a cosmologist specializing in dark energy dynamics. Together, the three published a systematic classification of every type of future singularity that general relativity permits, organizing the possibilities by which physical quantities remain finite at the endpoint. The classification sorts cosmic endings into four distinct categories. The first category is the Big Rip. At the moment of the singularity, the scale factor diverges, the energy density diverges, and the pressure diverges. Every macroscopic quantity describing the state of the universe shoots to infinity simultaneously, requiring phantom energy with W below -1 to produce. The Big Rip is the total singularity, the most extreme possible outcome in the classification. The second category is the sudden singularity that Barrow identified. Scale factor remains finite at the endpoint, and energy density remains finite alongside the scale factor. Only the pressure diverges. From a macroscopic standpoint, the geometry of the universe looks completely normal right up to the moment of termination. An observer with access only to the expansion rate, the temperature, or the large-scale density distribution would see nothing unusual in the final moments. A distinct intermediate case occupies the third category. Scale factor at the singularity remains finite, but both the energy density and pressure diverge simultaneously. Unlike the Barrow case, where only pressure blows up, the third type produces a thermodynamic catastrophe at the endpoint. Both the energy content per volume and the pressure reach infinity, while the spatial geometry of the universe stays technically bounded. The universe reaches a moment of infinite energy content, compressed into a finite size with no subsequent state the equations can describe. The fourth category is the strangest entry in the entire classification, and in some ways the most unsettling. Scale factor, energy density, and pressure all remain finite at the singularity moment. Even the first and second time derivatives of the Hubble parameter, the quantities governing the expansion rate and the rate of change of acceleration, remain finite. What diverges are only the higher derivatives, third order and above. A singularity of the fourth type, at the moment of arrival, produces no macroscopically observable consequence, no structure unbinds, no pressure spike occurs, and no energy density anomaly registers on any detector. From any observational standpoint, the universe simply continues evolving normally, and the singularity exists in the mathematics without manifesting in any phenomenon that any instrument, in principle, could detect. Nagiri, Odintsov, and Tsujikawa noted explicitly that fourth-type singularities may have already occurred in cosmic history. The universe could have passed through multiple fourth-type endpoints without any observer noticing. Whether a fourth-type singularity counts as a genuine ending, or merely as a mathematical feature of the solution, depends on how one defines the boundary between physics and pure formalism. The authors treated the question as genuinely open. The fourth type also raises a subtle philosophical challenge. A singularity that passes undetected by every possible measurement, in principle, cannot be ruled out by any observation. Physics normally defines real phenomena as events that produce, in principle, some measurable consequence. A fourth type singularity produces none. Whether such an object belongs to the physical world or only to the mathematical description of the physical world is not a question current cosmology can answer. Consider the scope of what this classification established. Before 2002, cosmologists had two endings on the table: a big crunch collapse driven by enough matter density, or a heat-death expansion driven by too little. Caldwell's phantom energy paper added the big rib as a third option. Barrow's sudden singularity result widened the threat to scenarios requiring no phantom energy whatsoever. Then Nojiri, Odintsov, and Tsujikawa's classification expanded the full picture to at least 4 distinct singularity types, plus the non-singular endpoint of heat death, each requiring different physical conditions to produce. The cosmos had more exits than anyone had mapped. Cosmologists had catalogued 4 types of universal ending with the dry precision of a geological survey team, logging rock strata. Each ending received a category number, and each number received a mathematical definition. The classification appeared in a peer-reviewed journal. The field absorbed the taxonomy, noted the thoroughness, and proceeded. That methodical quality should not obscure what the collection represented. Within 3 years of Caldwell's phantom energy paper, the model of possible cosmic endings had expanded from a binary to a full classification system, numbered and organized, waiting only for the measurement that would tell the field which category applied to the actual universe. Running alongside the singularity taxonomy was a separate line of investigation into the dynamical behavior of phantom dark energy over cosmic time. If phantom energy were a fixed parameter, the question of the universe's fate would reduce entirely to the initial value of W. Dark energy models built on scalar fields do not necessarily hold W constant, however. The field evolves as the universe expands, and whether weather can change over time opened a new dimension of possible behavior. Nojiri, Odintsov, and Tsujikawa examined whether phantom dark energy, once established as the dominant component, would remain stable over the subsequent evolution of the cosmos. The analysis identified what the authors described as a stable late-time attractor, a configuration where the phantom field settles into a fixed trajectory, maintaining W below -1 indefinitely, drawing the cosmological evolution toward a big rib endpoint, regardless of the detailed initial conditions. An attractor in dynamical systems theory describes a state toward which a wide range of initial trajectories converge over time. A stable attractor is self-reinforcing. Trajectories that begin near the attractor are pulled closer, and perturbations that push the system off the attractor decay away, returning the evolution to the same path. A stable attractor is, in a precise technical sense, a destination rather than a temporary configuration. The phantom attractor identified by Nojiri, Odintsov, and Tsujikawa carries a direct cosmological implication. When dark energy currently sits in the phantom regime, and when the phantom attractor is stable, the subsequent history of the cosmos does not depend, to any significant degree, on the precise details of the underlying scalar field model. Any model with a stable phantom attractor converges toward the Big Rip. Approach to the singularity is not sensitive to initial conditions, nor to the parametric details of the phantom sector. The endpoint is generic across an entire family of phantom models. That genericity is one of the more unsettling features of phantom cosmology. In most areas of physics, the precise details of a model determine the predicted outcome. Adjust the initial conditions slightly, and the trajectory shifts. Change a coupling constant, and the endpoint moves. The phantom attractor removes that sensitivity entirely, collapsing the diversity of possible phantom models into a single shared destination. A wide range of distinct models, built on different assumptions about the scalar field potential, the coupling to dark matter, and the initial field configuration, all flow toward the same terminal state. The Big Rip, under the phantom attractor result, is not a fine-tuned prediction. The Big Rip is a generic destination for an entire class of dark energy models. Separately, Luis Chimento and Ruth Lascaux, working on the mathematical structure of phantom singularities, examined how the Big Rip endpoint appears from the perspective of the singularity itself. The analysis probed the physical meaning of scale factor divergence not merely in the algebraic sense, but in the geometric and causal sense. Specifically, the singularity is space-like. Every point in space reaches the endpoint simultaneously, with no causal signal from any region, capable of arriving at any other region before the divergence occurs. Contrast this with the Big Crunch, that collapse moves inward toward a point, allowing distant regions to watch the process approach for millions or billions of years. In the Big Rip, no such warning exists at the cosmic scale, because every observer, regardless of location, reaches the endpoint simultaneously, with no possibility of lateral communication in the final instance. The taxonomy described 4 types of endings. The attractor analysis suggested that phantom models, over cosmic time, tend to converge on the most total of those endings. And then Nojiri and Odintsov, in a separate paper from 2003 predating the full classification work, pointed to a possible escape. The paper was titled Quantum de Sitter Cosmology and Phantom Matter, and the argument began from a well-established result in quantum field theory, the conformal anomaly. When a quantum field propagates through a curved space-time background, a subtlety arises in the renormalization of the energy-momentum tensor. The classical action of a conformally invariant field vanishes under scale transformations. The quantum version does not. A residual term survives the renormalization procedure, proportional to geometric quantities constructed from the curvature of space-time. This residual is the conformal anomaly, also called the trace anomaly or Weyl anomaly. The anomaly generates a contribution to the energy density and pressure of the quantum field, a contribution that has no classical counterpart. In flat spacetime, where spacetime curvature vanishes, the conformal anomaly contribution is 0. Near a Big Rip singularity, curvature diverges. As the scale factor approaches infinity and the Hubble parameter grows without bound, the curvature terms entering the conformal anomaly become large. Nojiri and Odintsov calculated the contribution of the conformal anomaly to the Friedmann equations in a phantom-dominated universe. The quantum correction terms the analysis found grow in proportion to the square of the Hubble parameter and to the cube of the Hubble parameter. The practical consequence is significant. During the early universe and in the present epoch, the Hubble parameter is small enough that the conformal anomaly correction is negligible compared to the classical energy density. Classical general relativity describes the expansion with excellent precision, and the quantum correction sits buried far below any observational threshold at this stage. As the Big Rip approaches and the Hubble parameter diverges, the quantum correction grows rapidly with each passing epoch. At some point, the the correction terms become comparable in magnitude to the classical phantom energy density, and at that moment, the quantum correction changes the character of the solution. Nojiri and Odintsov found that the combined system, classical phantom energy plus quantum conformal anomaly correction, can be driven toward a de Sitter fixed point rather than a big rip singularity. A de Sitter fixed point is a stable state of exponential expansion at a constant Hubble parameter, exactly the behavior associated with a cosmological constant. Rather than the Hubble parameter diverging to infinity as the big rip approaches, the quantum correction provides a stabilizing pressure that flattens the divergence, pushing the evolution toward a constant expansion state that continues without reaching a singularity. Whether the conformal anomaly actually prevents the singularity depends on the magnitude of the quantum correction relative to the classical phantom energy density and on whether additional quantum gravity effects not captured by the anomaly calculation modify the picture. Nojiri and Odintsov describe the result as a moderation, not a prevention. The conformal anomaly calculation is valid only in a regime where spacetime curvature is large, but the full theory of quantum gravity is not required, a calculation that holds when curvature is high, but not yet Planckian. Near the Planck scale, all such calculations break down, and the behavior of the singularity in that final domain is genuinely unknown. The quantum correction opens a door. Whether the door leads to safety depends on physics that no one has yet fully worked out. The conformal anomaly calculation establishes that a correction exists, that the correction grows as the singularity approaches, and that the correction is large enough in at least some parameter regimes to alter the endpoint of the evolution. Whether that alteration is sufficient to prevent every type of singularity under every set of initial conditions remains genuinely open. A deeper problem also exists. The conformal anomaly is a result from semi-classical quantum field theory, a framework that treats spacetime geometry as a fixed classical background, while allowing quantum fields to propagate through that background. That approximation is justified when background curvature is large by ordinary standards, but small compared to the Planck curvature. As the big rip singularity approaches, background curvature eventually reaches Planck scales, and the semi-classical approximation breaks down. At that stage, a full theory of quantum gravity is required. No such theory currently exists. Phantom energy as a classical scalar field may not be the correct underlying description, even if W below -1 is the correct description of the observational signatures. Nojiri and Odintsov noted that phantom behavior can emerge as an effective description from quantum field theory models that do not require a fundamental scalar field with a reversed kinetic term. The same observational signatures, the same acceleration history, and the same equation of state could in principle arise from quantum corrections to conventional scalar field dynamics. In that case, the big rip singularity would be an artifact of applying the classical field description beyond the validity range of that description, rather than a genuine prediction of the underlying quantum theory. That possibility is not a resolution. Rather, the possibility is a reframing of the uncertainty. Whether the big rip is prevented by conformal anomaly corrections, replaced by a de Sitter attractor, or dissolved by the breakdown of the classical phantom field description, the common feature is that the answer lies in a domain of physics, high curvature quantum gravity, where no complete theory currently exists. What the taxonomy could not resolve was the most fundamental question of all: which ending, if any, applied to the actual universe? Every type of singularity described by Nojiri, Odintsov, and Tsujikawa requires specific conditions on the dark energy equation of state and on the behavior of the phantom field over cosmic time. Sustaining W persistently below -1 and drawing toward the phantom attractor is required for the big rip. The sudden singularity requires specific conditions on the scale factor exponent, conditions that do not necessarily involve phantom energy at all. The intermediate and higher order types require conditions between those extremes, and the quantum correction that might prevent the most violent singularity depends on a calculation that is only valid in a specific approximation regime. All of those requirements converge on a single observational question: what is the precise value of W? That question had no clean answer in 2005. The same question had no clean answer in 2011, when Frampton, Ludwig, and Scherer added the Little Rip to the catalogue. And the same question has no clean answer now. Every path through the singularity taxonomy, every variant of the phantom attractor analysis, every quantum correction calculation returns eventually to that single numerical threshold, separating the cosmological constant from phantom territory and to the measurement uncertainty that prevents any instrument from resolving which side of the threshold the universe currently occupies. Quantum mechanics might save the universe from the Big Rip, or quantum mechanics might offer an entirely different ending, one without a singularity at all, but no less total in the destruction. The answer arrived in 2011, and the answer was worse than the question. The quantum conformal anomaly correction, developed by Nogiri and Odintsov, offered a mechanism by which the growing curvature near a Type 1 singularity could push the evolution toward a stable de Sitter fixed point instead of a divergence. That possibility represented a genuine potential escape from the most violent entry in the singularity catalogue. But the escape route, if real, addresses only one specific type of ending. The full catalogue contains 4 types, and in 2011, Paul Frampton, Kevin Ludwig, and Robert Scherer added a 5th scenario to the list, one that produces no singularity at all, no divergence in scale factor, no infinite pressure, no moment where the equations refuse to continue. The destruction happens anyway. Frampton, Ludwig, and Scherer published the Little Rip analysis in Physical Review D. The starting point was a question the community had largely bypassed. What if the dark energy density increases without bound over infinite time, rather than at a finite moment? The Big Rip requires the scale factor to reach infinity at a specific calculable time in the future. The conformal anomaly correction might prevent that specific finite time divergence, but preventing the finite time singularity is not the same as preventing the destruction of all bound structures. The two outcomes are not equivalent. A universe undergoing Little Rip evolution has dark energy with W below -1, just as in the phantom Big Rip scenario. The energy density of Little Rip dark energy increases without bound as the universe expands. But the rate of increase is slow enough relative to the expansion rate itself that the scale factor never reaches infinity at a finite time. The singularity is deferred, stretched asymptotically toward infinite future time, and in the formal mathematical sense, never arrives. In the formal sense, not in the physical sense. Frampton, Ludwig, and Scherer reframed the question around inertial force rather than scale factor divergence. The relative acceleration between any 2 points in an expanding universe depends on the expansion rate and on the rate of change of the expansion rate. For any 2 particles separated by a distance and bound to each other by some constant force, whether that force is gravity, electromagnetism, or the strong nuclear force, the expansion exerts an inertial force tending to separate the 2 particles. When the inertial force exceeds the binding force, the 2 particles decouple. The bound structure dissolves. In the Big Rip scenario, the inertial force diverges at a finite time. Galaxy clusters decouple first, then progressively smaller and more tightly bound structures until atoms and nuclei dissociate in the final fractions of a second before the singularity. The sequence is catastrophic, but the timeline is finite and calculable. In the Little Rip scenario, the inertial force also grows without bound, not at a finite time, but over infinite time. The rate of growth is slower than in the Big Rip case, but the direction of growth is identical, upward, without limit. At some point, the inertial force will exceed the gravitational binding energy of galaxy clusters. The clusters will dissolve. At a later point, the inertial force will exceed the binding energy of individual galaxies. Those galaxies will dissolve. The sequence continues through the same hierarchy of structures as the Big Rip, dismantling the cosmos layer by layer, each step separated from the previous one by a longer interval, but each step arriving with mathematical certainty. Atoms will dissociate. Nuclei will dissolve. Every bound structure in the universe will eventually be pulled apart by the growing inertial force, not at a finite singularity moment, but over an infinite timeline. The practical difference between the Big Rip and the Little Rip for any finite bound structure that exists in the universe is zero. Both scenarios end with the complete dissolution of every bound structure ever assembled by any force in nature. The Big Rip accomplishes the dissolution at a specific, calculable moment. The Little Rip accomplishes the same dissolution over an unbounded future. The universe in the Little Rip scenario has an infinite lifetime. None of the structures inside the universe share that infinite lifetime. Frampton, Ludwig, and Shatter also examined whether coupling between dark matter and Little Rip, dark energy, could alter the outcome. In the Big Rip case, Nojiri and Odinsov had shown that coupling, specifically the decay of phantom dark energy into dark matter, could prevent the Big Rip singularity and drive the evolution toward asymptotic de Sitter space. Frampton and colleagues investigated whether the same coupling mechanism could eliminate the Little Rip. The answer was conditional. Under certain coupling parameters, the dark energy decay rate balances the growth of the dark energy density, and the expansion history converges toward a de Sitter fixed point rather than a Little Rip. The Little Rip in those models is avoided entirely. Whether that coupling exists in the actual universe is unknown. The coupling is not a prediction derived from any observation. The coupling is a parameter in a model, adjustable to produce a range of outcomes, and the observation of dark energy provides no constraint on whether the coupling is present, absent, or set to a value that matters. The Little Rip introduced something important beyond the specific physics of the scenario. The Little Rip demonstrated that the Big Rip singularity was not the only mechanism by which phantom dark energy could eventually destroy all bound structures. The singularity itself, the moment of infinite divergence, was separable from the destruction. A universe could dismantle every galaxy, every star, every atom, without ever reaching a mathematically singular state. The destruction was not a consequence of the singularity. The destruction was a consequence of the growing dark energy density, and the singularity was simply the most dramatic version of that consequence. That separation matters for the quantum correction argument. If quantum effects prevent the finite time singularity, but do not prevent the indefinite growth of dark energy density, the result is not a safe ending. The result is a Little Rip, with the same ultimate outcome as the Big Rip, merely stretched over a longer timeline. Quantum mechanics, in that scenario, modifies the schedule of destruction without altering the destination. One more potential escape route deserved examination. Wormholes, topological features of space-time connecting distant regions through shortcuts in the geometry, had been proposed as a possible mechanism by which matter or information could escape a universe approaching the Big Rip. The argument seemed compelling at first glance. If phantom energy weakens gravitational attraction and allows extreme topological configurations to persist, perhaps a wormhole throat could expand faster than the surrounding universe, engulfing the approaching singularity and providing a passage to another region of space-time before the Big Rip arrived. The physics, analyzed carefully, does not support that picture. Valerio Fararoni and Werner Israel, working at Bishop's University and the University of Victoria, modeled the evolution of a wormhole embedded in a Friedman universe approaching the Big Rip. The wormhole was modeled as a thin spherical shell accreting phantom fluid from the surrounding space-time. Two distinct wormhole models were studied, representing different assumptions about the structure of the wormhole throat. Both models produced the same result. As the Big Rip approaches, the wormhole throat does not expand faster than the surrounding cosmic fluid. Instead, the wormhole becomes asymptotically commoving with the cosmic fluid. A commoving object in an expanding universe maintains a fixed commoving coordinate position, expanding with the surrounding space rather than growing relative to that space. The wormhole throat tracks the expanding background geometry, staying in lockstep with the surrounding phantom fluid rather than overtaking the expansion. The wormhole does not engulf the universe. The wormhole does not provide passage to another region. The future evolution of the space-time is fully causal, meaning that no signal from the wormhole region propagates faster than the surrounding expansion, and no exotic causal structure develops that would allow any observer to escape the approaching singularity. The conclusion of Fararoni and Israel was direct. The existence of a wormhole in a phantom universe does not alter the ultimate fate of that universe, and no observer inside the wormhole gains any advantage over an observer outside. The escape route through wormhole physics closed. at the same moment the calculation was completed. Consider what the complete picture looks like at this stage. The Big Rip, if W sits below -1, arrives at a calculable time, destroying every bound structure in a precise countdown. Galaxy clusters a billion years before the end, the Milky Way 60 million years before, the solar system 3 months before, the Earth 30 minutes before, and individual atoms in the final 10 to the power of -19 seconds. The Little Rip, if the dark energy density increases over infinite time, produces the same eventual destruction without a finite time singularity. The Barrow sudden singularity can terminate the universe with no phantom energy required and no observable warning. The full Nogiri-Odintsov Tsujikawa taxonomy classifies 4 distinct singularity types, each requiring different conditions, each producing different physical signatures, and one of which may have already occurred without detection. Quantum corrections can moderate the Big Rip singularity, but the correction relies on a semi-classical framework that breaks down before the final Planck scale approach, and the same corrections do not necessarily prevent the Little Rip. Wormholes, as Ferroni and Israel demonstrated, become commoving with the surrounding cosmic fluid as the singularity approaches, providing no passage to any safer region of space-time. Every exit has been examined, none of them hold. Every scenario in the catalog, every singularity type, every alternative ending, every potential quantum rescue converges on a single point of contact with observation, the value of WW. The constraint on W from current observational data comes from combining multiple independent probes. Type Ia supernovae at high redshifts constrain the relationship between luminosity distance and redshift across a broad range of cosmic history. The cosmic microwave background power spectrum constrains the geometry of the universe and the total dark energy fraction. Baryon acoustic oscillations, measured in galaxy surveys, provide a standard ruler for cosmic distances at multiple redshifts. Weak gravitational lensing surveys, mapping the distribution of mass across large patches of sky, provide additional constraints on the growth of structure. Each of these measurements contributes information about dark energy, and the combined constraint places W at approximately -1.03, with uncertainties of roughly 0.03 in either direction. The central value sits slightly below -1, inside the phantom regime. The error bar, however, comfortably encompasses the cosmological constant value of exactly -1. The gap between W equals -1 and W equals -1.05 is not large in absolute terms. The two values differ by 5/100ths of a point. That is the entire distance between a quiet ending and a violent one. Across the entire history of human mathematics and measurement, a difference of 5/100ths would barely register as a concern. In the context of cosmic fate, that gap is the boundary between two categorically different futures. At W equals -1, the cosmological constant holds. Heat death unfolds over trillions of years, and every atom ever assembled by any star survives intact forever. At W equals -1.05, phantom energy dominates. The dark energy density grows with each passing epoch, and every structure in the universe, from the largest galaxy clusters to the quarks inside individual protons, carries an expiration date. No existing instrument can resolve the measurement to that precision. The 5/100ths gap falls inside the current error bar, and no planned observatory, with the survey strategies and detector capabilities known today, will close that gap completely within any foreseeable time frame. The current best constraint on W comes from combining Type Ia supernovae, the cosmic microwave background, baryon acoustic oscillations, and weak gravitational lensing. Each of those probes measures a different aspect of the cosmic expansion history, and each contributes a partial constraint. The combined constraint achieves a precision of roughly 3 to 5% on W. The difference between the cosmological constant and a phantom equation of state capable of producing a big rip within the next 22 billion years requires measuring W at a precision closer to 1% or better, depending on the specific phantom model assumed. Current surveys are not there. Planned surveys will improve the situation, but the margin of remaining uncertainty is not small. The James Webb Space Telescope extends supernova surveys to higher redshifts, improving the constraint on the expansion history in the early universe. The Euclid mission, surveying baryon acoustic oscillations across 1 billion galaxies, will reduce uncertainties on the dark energy equation of state. Next-generation weak lensing surveys will tighten the constraints on structure growth. All of these improvements push the measurement precision forward, and all of them will still leave a residual uncertainty. Will that residual uncertainty ever shrink below the threshold needed to resolve the question? The physical limitation is not simply instrumental sensitivity. Part of the difficulty is that dark energy interacts with ordinary matter and radiation only through gravity, and gravity on cosmological scales is measured through the geometry of the universe rather than through direct detection. Think of trying to weigh a gas by measuring how a floor sags beneath a room. The sag is real, but the inference from floor curvature to gas mass passes through the stiffness of the floorboards, the furniture load, and a chain of structural assumptions. More precise measurements of the floor cannot eliminate that chain. Every measurement of W is therefore indirect, inferred from the geometry of an expanding space-time rather than from any laboratory interaction with the dark energy field itself. The inference chain from raw observational data to a constraint on W passes through multiple modeling assumptions, each carrying uncertainty, and the accumulated uncertainty from those assumptions places a practical floor on how precisely W can be determined from any cosmological observation. The uncertainty is not simply a matter of measuring more supernovae or surveying more galaxies. The equation of state of dark energy may not be a static quantity. If W evolves over cosmic time as quintessence models permit, then measuring W at the present epoch does not determine what W will be in the distant future. A universe where W currently sits at -1.02 could evolve toward -1, stabilizing at the cosmological constant. The same universe could evolve toward -1.1, deepening into phantom territory. Distinguishing these trajectories requires measuring the rate of change of W over cosmic time, a task that demands precision beyond any current survey program. Every cosmic fate scenario, every singularity type, every quantum correction, every alternative ending reduces to one number. The equation of state parameter, W, and the measurement that would settle the question has not yet been made. The universe is doing something. Right now, in every cubic meter of space, dark energy fills the vacuum with a pressure and an energy density that no direct observation has ever measured. The expansion is accelerating. The rate of acceleration is constrained within error bars to a value consistent with either the cosmological constant or phantom energy. The transition between those two cases, the crossing of W below -1, would commit the cosmos to a countdown that has already been calculated in detail. The countdown exists in published equations, derived from the Friedmann equations under specific parameter assumptions, with every entry verified against the orbital periods of real astrophysical systems. The countdown may be running, or the countdown may not exist. The difference between those two possibilities is a number that sits inside an error bar, and the error bar is smaller than the error bar was in 2003, and smaller than the error bar was in 2011, and still not small enough to resolve the question. The measurement has not been made. The countdown may have already started, and the uncertainty for now is the only honest answer physics can offer. 30 minutes. That was the number for Earth. Not a metaphor, not an approximation drawn from vague extrapolation, a specific interval calculated from a differential equation derived from observable orbital periods and a single equation of state parameter. A physicist sat down with the Friedmann equations, pushed the value of W below -1, and read the answer. 30 minutes before the space inside every rock, every ocean, every iron core rips outward faster than the electromagnetic bonds holding matter together can resist. The number exists in a published paper. The paper exists because the mathematics permits the result. The 1998 discovery revealed that expansion was not decelerating. Phantom energy revealed that the expansion could accelerate without limit. The singularity taxonomy revealed that the universe has more ways to end catastrophically than anyone had mapped before 2002. The little rip revealed that even escaping the singularity does not escape the destruction. Every discovery after 1998 either deepened the crisis or widened the catalogue of possible endings. Every path through that catalogue converges on one measurement that has not yet been made. That is what this documentary has actually been about. Not the countdown, not the catalogue of endings, the gap, the 500ths of a point separating a quiet fade from a violent disassembly of every proton in existence. The error bar that contains, simultaneously, the cosmological constant and phantom energy, and every fate that follows from each. Physics produced the most precise destruction timeline ever written, and then disclosed in the same calculation that the measurement required to confirm or refute that timeline exceeds the precision of every instrument currently operating. The uncertainty is not a failure of science. The uncertainty is the honest position of a discipline that derived the countdown before the cosmos revealed which side of the threshold dark energy actually occupies. Science ran the calculation first. The universe has not answered yet. A single point of light in an expanding void, the distance to the nearest neighbor growing imperceptibly wider. Tonight, that widening is harmless. The question physics cannot yet resolve is whether tonight looks any different from the first night of the countdown. What we have just uncovered is not just a fact about the Big Rip. The discovery is evidence that our intuitions about cosmic stability are completely wrong. The universe runs on rules that feel alien, and that gap between what we assumed and what the equations actually show is precisely where science thrives. If you want to help improve the quality of this channel, like and subscribing goes a long way for our channel. The channel exists because of viewers who care enough to support work like this, and that support genuinely changes what becomes possible here. If you know someone fascinated by the fate of the universe, send this video their way. Sharing is the best way to help this community grow. Every new person who finds the channel means, in a direct sense, more stories like this one can be told. I will catch you in the next one. Let curiosity guide you, keep learning, and know that you are always appreciated.